Yeah. Okay. Thank you, guys. Let's find a SGD example. Oh, just kidding. I think a picture will explain that pretty well. Um, so let's look at this picture. What does it mean? We have, so the first question would be, what are the parameters in this model or function? So we have two parameters, right? We have theta 0 and theta 1. And then what does this J mean? It, I think they named it energy, but really it's the loss function of our model. So there are a few terms that we need to clarify. Sorry, it's raining. I need to close the window. All right. Yeah. So essentially, what is the objective function? Usually, it's the you know the one way to look at it usually is the mean squared error, right? In regression, we have the MSE being the loss function of our regression task. That is also, you can also call it the loss function. Basically, it's the your prediction and the true value. The difference between your prediction and the true value squared for all predictions is your loss function. In this case, J means how far you are away from the objective. And obviously, the smaller your loss is, the better your fitted model works. So ideally, if you know the analytical solution to this function, so J, or the loss function, is a function, and it has a global solution. It has an argmax of theta 0 and theta 1 such that J of this is minimized. There is only one out there, and then which is this, which is when theta 0 is 0.4 and the theta 1 is 0.8. And then, but for most of machine learning tasks, we don't need the best. We just need something to work. And then if you use that, it would also work, but not as well as that. So with most of the tasks we're doing, such as this classification task, how does this translate into this picture? Is what we need to define, right? In this case, what are our theta 0 and theta 1s? Our theta 0 and theta 1 is the pixels of the picture. So in this case, there are 32 times 32 times 3 parameters. That is a very high dimensional space, right? And we can no longer visualize it like that. But just imagine it being in a higher dimension. Our objective function, which is so that is the parameters. So that's our input space. So let's define. So let's think about the problem. How do we define the loss function for a classification task? Let's say we do classification on this image. I think it's a plane, but instead, our model predicts it to be a bird. How far away are we from the true answer? It's hard to quantitatively say how far we are away, right? This is where we need to use something called the cross-entropy loss. So, all right, let's be a bit slower. So, what should our model tell us for each of the images given? The models we use should tell us 10 predictions for each class ideally our model tells us a probability the the picture is in that class. So that unit, I think, is called the energy of a class. Basically, we have an energy prediction for each of the classes, and at the end, we predict it to be the class that has the highest energy. So simplifying that into math, we're given an image and then we're predicting 10 numbers. Those 10 numbers are the energy predictions. Similar to this, so our predictions are values between roughly -3 to 3. But what are our true values? Ideally, so our energies can be translated into pseudo probabilities with the softmax function. Let's take a look at an example. Let's just do NumPy. So random. So imagine our network predicts 10 values. And so this will be the energy for the first class. What is that? For airplane, and then for everything else. How do we translate that into how do we translate that into pseudo probabilities? So ideally, I want higher energy to have a higher probability of being the true class, a lower energy with a lower probability of that class. So let's take a look at x. X is this values. But with the softmax function, it will scale that into a pseudo probability. Vector. All right. Yeah. Okay. So let's take a look at x. So as we can see, I think this value is biggest, right? Yeah. And then this will be a probability of 0.24 being in one class. Is one of these. So, and then for our prediction, we're going to use the largest energy as our final prediction. So going back to the optimization. So usually when we start a model, we start at a random place, right? All the weights are randomly generated, meaning theta 1 and theta 0 are randomly generated. So you're spawned at any point on the graph. With usually you probably usually hear about updates, right? Weight updates. What weight update is doing in geometry is that you're moving on the curve. I guess that's not the best way to explain it. You're actually moving on this bottom plane. You're not moving on the. You can also look at it like that, but every time you move on the parameter space, you want to move in the direction such that it minimizes the loss function the most, and this requires an update scheme. Usually, so there are a couple of trade-offs here. What are the computationally intensive operations that's happening here? I think the most expensive computation is that. So first of all, you want to find the direction of your update, right? That's that's the most expensive thing to find. Especially so in 2D, you only have two directions you have to decide. That's two vectors. Two scalars, right? You only need to specify two scalars so that you know which direction you should update your weight. However, uh, images have a lot more dimensions. So each dimension needs a scalar of the update, and that would be kind of expensive. Okay, so, and then there's also something in numerical analysis. How much should we move? Like, what's the learning rate of each update? Usually, the learning rate in deep learning is set as a hyperparameter. But in traditional stats, that learning rate can also be learned, right? There is only one optimal learning rate, such that you can move any point to the global minimum with one update. That learning rate exists, but finding that learning rate is also a very expensive operation. So deep learning is trying to find a trade-off between these two so that you can move along in space with relatively cheap operations. And then the trade-off is that you don't get the best loss. You don't get the best final result every time you're kind of wandering around and getting trapped in a local minimum. Okay. I think that's the big picture of any deep learning problems. All right, let's look at this example. All right, so let's explain the data set a little bit. This is a pretty simple data set. These are extremely blurry pictures of 10 classes, and our job is to classify them. Oh yeah, there's a simple thing we can talk about is that how do we count the number of layers in a model, right? So imagine this as a neural net. It has two convolutional layers. The pooling layer, for some reason, doesn't count as a layer, but the fully connected do count. So this is a 5-layer neural net. All right. So what's the stochastic gradient descent? So it goes back to the matrix operation problem. Right? There's an idea of batch size. So I don't know if I should go into this. Let's talk about something easier to understand.
I can explain this one. So in gradient descent, the traditional gradient descent takes all the images together, all the data you have, and it takes in gradient descent calculate the gradient and update in that direction towards the true distribution. So what happens is that's very computationally expensive, and you don't want to do that, especially when you have really large data sets. So what we do is something called stochastic gradient descent, where you operate on batch, which batch is a subsample of the amount of data. Usually we choose basically as much as your memory of your GPU or CPU can handle. And so it's a little less optimal, but the SGD goes towards some suboptimal solutions that will work for your task for a computational reason.
Yeah, it's solely for a computational reason. As we can see, if you do gradient descent, every time you find the optimum update, right? So what does this mean? The darker colors are lesser loss. So we're trying to go to lesser colors, darker colors. With stochastic gradient descent, we're not looking at the whole data set. We're looking at a batch, meaning a randomly selected set, smaller sample set of the whole data set. So with with a small data set, you can compute anything faster. And then with the key point is that you randomly select, so they're representative of the bigger population set. So mathematically, it converges to the same thing because they're representative. But you're dealing with larger variants, so you have to do a lot more updates to eventually converge. So as you can see, a gradient descent uses a whole set, so it for sure updates the optimum. It follows, I think it should be perpendicular to the contour curve, but stochastic gradient descent, it's traveling in a sample space, so it's not representative of the actual objective function. It's a sample of the actual objective function, and this is the same graph, I think. So as your batch size increases, the more stable it gets for each update, but it's more expensive that way because every matrix operation is at least n squared. So you don't want it to be too large, otherwise it takes too long. Okay. Cross-entropy loss is, I think, is using binary classification. Basically, if you're closer, so you're predicting a pseudo probability, right? You're predicting a probability, and the true values is not a probability. It's a true value is either 0 or 1. So let's say the true value is 1, and then you predicted 0.9. How much should you get penalized? So we use the log function, right? And vice versa. Like if the true value is 1, you predict 0.6. How much more should you be penalized than if you predict 0.9? So that is the cross-entropy loss. All right. So what is training the network? Training the network is basically you're tweaking the weights until you hit a combination of weights such that it predicts the right probabilities every time. Not every time, as much as you can. So if we don't talk about the code, we should probably still look at the so training is just another term for optimizing the weights, right? That's why you need an optimizer. Okay. So imagine we don't have deep learning, right? How do we do classification with traditional stats method? So we have to explicitly code features in the image such that it predicts the right task, right? That probably works better than deep learning, but it costs a lot of human time to find these features and also implement them. And then you also suffer from generalization because if your features are not generalizable, it only works for a certain set of, for example, birds. If the birds looks weird or like a new kind of bird, it wouldn't work. So that's why deep learning is desirable in that kind of sense. Anyways, all right. So let's just discuss what other things you might see about. Oh yeah, I have a question for you guys. Is that we usually see the word kernel in a lot of our methods, right? What is the kernel, and how does that relate to the kernel in mathematics? What do you guys think? Hey Charlie, can you give a short talk about convolution? Dang it, I think Charlie's AFK.
Okay, I can try to do it. So let's see. So let's say that you wanted to try to find one moment. Okay. So if you think of an image as like as its intensity values at each point, then you want to consider like the amount of noise in the image and the different counter patterns that are in an image. And the best way to do that is kind of to have a lot of pictures of an image, but you only really have one. So what we do is we do something called some image filtering that uses some kernel, which the term filtering kernel are kind of synonymous. And these kernels, when you multiply them with the original image, it'll create some new representation of an image. It might enhance it, it might blur it, but both of which are kind of useful for the image itself. And so one of which is called the convolution. And there are two ways to multiply an image with the kernel. And one of which is called convolution, and the other one's called cross correlation. And they're really similar. And I want a better picture than that though.
Yeah, you want to share? I think if I stop sharing, the recording stops.
Yeah, stop sharing. Just look at a picture.
Oh wait, I can open up. Just kidding. Go ahead.
I can share?
Yep.
Are you serious?
Yep. Oh, Simon's saying something. Kernel is a set of domain, which when applied to a function give 0. Oh yeah. It's a different. So that kernel I think is the the vector space kernel, right? So yeah, linear algebra and abstract. I think we're interested in the kernel function in machine learning.
Can you last screen share?
Yeah. Yeah, it's not that kernel, I think. But yeah, that is also a valid kernel. You can share. All right, Charlie, go ahead.
So so there's two sets of operations you can do on a let's see. So I can think of myself. The reason why we use these kernels is because that they allow some representation of the image to be known. So there's an image processing, but they allow us. I cannot find an example right now. When the kernel allows you to find for example, I cannot explain this stuff.
Okay, so
it allows you to find a limited combination of the elements around some local batch. So for this reason, when you do the convolution neural net, you go through, you slide through each part of the image as a convolution operation. It'll allow you to, for example, learn features on a smaller scale. I cannot explain this stuff.
So I think so. Usually we define the product of two vectors as the dot product, right? So
I cannot explain this stuff in my head.
Yeah,
Sorry.
I think. Yeah, I'm not entirely sure about the kernel function because I think there's some mathematical intuition behind it. It's that helps in.
I'm sorry, that was my fault.
Yeah. Okay. So, yeah, this is the example you learn about if you take the class, but usually when we're multiplying two vectors, um, we can't multiply vectors because they have dimensions. And the one thing we use is the inner product, where we multiply each element and then sum them. That is not generalized, because why do you sum them? Why can't you multiply them? Why can't you, do other things? Um, this is where kernel is, I think, is more generalized kind of inner product between any two vectors. And with one trick, um, you can usually uh, up your number of dimensions with a lot less computation. For example, you're doing one dot product here of two by two, right? And then at the end, you get a six dimension feature with only two, like the worth of two dimensions computation work. Um, and then there's some math intuition about something called the kernel matrix or the gram matrix. If this matrix is semi-definite, then you have a valid kernel function, such that um, so this kernel function basically can be separated into two different kernel functions multiplied together. Um, and at the end, you always get a scalar for any kind of inner product, right? It's just a different way of doing inner product. And then convolution is one way of doing this. Um, so let's describe what convolution is doing. I think Charlie explained pretty well. You have a mask, or this thing. The mask size is a variable. You can change it to bigger and smaller, and then you can slide it uh, every 2 grids, every 3 grids. That's the stride size. You can also change that. Anyways, it's a way of doing dot product, such that after you do the dot product, you get a scalar on the next layer. So um, what kind of dimension is it? It's actually scaling down, right? So convolution goes from a higher dimensional space to a lower, usually. And then there's also something called deconvolution, that you go from lower dimension to higher. Um, and something like, I think Charlie talked about like transpose something.
So if we
Yeah,
look at, can we look at this picture? What you're doing with two slides before, or whatever. So actually, for a kernel, or for a filter of this, this is actually what we call the cross correlation in a signal. And we multiply by an image by some filter like this. And what you do is you slide through and you take through multiply by the inner products and add them together, or take the inner product and you compress the image that way. Actually, what the term convolution means is to first rotate the kernel horizontally and vertically, which is like a diagonal transformation of the kernel, and then to slide across and multiply. So when we say something like the convolutional neural net, we're actually saying it's a cross-correlated neural net. But the reason why is because we don't really care what the kernel looks like. We don't care if it's diagonal, horizontally transformed. We're just saying that the kernel doesn't particularly matter. It's the ways of the network that are learned that are more important. So the term convolution is a kind of a misnomer, if that makes any sense. And there's also something called the deconvolution. And the deconvolution is, instead of downsampling, you're upsampling. You're trying to get to a larger image size. And to do that takes a lot more computational work. And to fix that problem, what we do is we do zero padding around the image. And we introduce a number of zeros around the whole image, and we work backwards to find a larger image size. And what that does is it's not a true deconvolution. So we call this a transpose convolution.
Yeah. I think so. So why do we need convolution and deconvolution usually? It's for a segmentation task, right? Or you can use it for picture generation. In our some of the new phones, they add this kind of GAN network so that your pictures gets auto. Some of the details, if it's blurry, auto generates. It makes your pictures more clear. by generating fake stuff that doesn't even exist, but it makes it look, with looks higher resolution. For example, you take a blurry picture of the moon, right? And it identifies it as the moon. So it will automatically match results from the already stored data. And then it's not really the thing you saw in the moon, but like past pictures of the moon. They combine these together and generate clear pictures of the moon, even though you didn't take a clear picture of the moon. The same as so this uses GAN, right? It's generating objects with similar traits. So generating requires, so first you need to formalize and you need to formulate a abstract idea. So the moon, right? The moon is an abstract idea, and then it corresponds to an array of pixels such that it looks like a moon. That's a higher dimension but lower abstract level of the moon. So I think it would make more sense to look at the auto encoder and feature learning. So our input is the picture of blurry stuff that we took. But from past experience, we know that there are some higher features of the moon that we learned from past data, and then we can generate a new picture of the moon such that it incorporates what others have into your blurry image. So then it kind of denoises your image, or it generates stuff that it's not really real, but it makes your picture clear. So this involves deconvolution here, because you want to go from abstract, low dimension stuff to more concrete, high dimension stuff. That involves all the things Charlie just described. You have zero paddings, and how to reverse the process of convolution. Basically, you just do everything opposite, but because the loss of information, you need to also generate some sort of stuff from previous layers. And that's the main idea of deconvolution. Ideally, deconvolution is lossless, which means you do it forward way and then you do it backwards, everything gets preserved. However, it's very hard to do that. Not all the data involves, if that only happens if your convolution is the exact inverse of your deconvolution, which is rarely the case given that all these weights are constantly updated and they're not strict inverse of the previous weights. So you definitely have information loss in this process. Deep learning needs to solve this problem by using, usually the introduced method is a skip connection, where it directly just matches what it was before, like as an identity mapping. So, and then there are a ton of ways to solve this, but they're all not perfect. And then more, but better kind of methods are being researched to solve this. Anyways, so I think just concretely, for our task, we can just invoke what's already there. Usually, what's that? I think it was like a UNet or some sort of other net that you can call so that they directly do this for you. But know that these methods have limitations, and that what information is lost and what we might be able to do to improve them. So yeah, I think I got asked once on, let's say you have a network that does classification. How can you turn that problem into, maybe generate I think it makes more sense to talk about GAN, right? Okay, so this is GAN, right? It's kind of blurry. Okay, let's just use this image. All right, so so let's say we want to be able to generate a moon, right? We need some old pictures of the moon first, so that we have stuff to study from, and then so we can imitate what it looks like and then generate fake pictures. Those old pictures of the moon are real world images. Um, they're passed in as samples for the discriminator to learn. And so since we know it's real, this part of the training is supervised, right? If the discriminator predicts wrong, then we need to update that. So let's just look at the top half. If we only train this, what are we doing essentially? So we pass in real world images. We can pass in moon and not moon, right? Essentially, our oh yeah, like in the GAN network. Let's say we only train the generative. I mean the adversarial part.
Is it just memorizing or?
Yeah, let's delete. Let's say we prune all this thing, and yeah, just the top half is there. What images are we passing in first of all? So let's pull up an equation, and then we can talk about the math later. Anyways, so we're training a discriminator basically. This is the exact same as this, but you have one class, the moon, right? So it's called a discriminator, but you don't have to really call it the discriminator. It basically classifies either it's real or not real. So like on or off. That's the same as giving a prediction here. If it's on or it is a plane or it's not a plane. So essentially, if you train this really well, like train this perfectly, you pass in a moon, it tells you true, and then you pass in a not moon or fake picture of the moon, it tells you false. But we don't just want to be able to classify it. This this top half is only a classifier, a supervised classifier. But we also want to be able to generate, right? Generate new pictures that are fake, but it looks real. So we also need to train a generator network. So notice there are two networks. Nothing more than that. Only weights inside of these needs to be trained. The structure is already fixed. So how do we generate fake pictures? Latent random variables. So you need to define a set of, well, what is the latent variable? It's kind of the representation of moon. Let's say it's a circle. It's like all the high level abstract stuff. It's nearly white. It's in the center of the image, or above the tree, or like all the abstract level stuff. The dimension of this is really small compared to the pixels in the image, which is a very high dimension stuff. And then we generate this is basically you go there into into an image. All right, let's look at the objective function. Oh, come on. All right, we're now going to worry about encryption. Okay. Yeah, okay, this is a much better picture. So the training set, let's look at the moon again. I guess let's look at the numbers. So these are real numbers. Okay, it's making it complicated because they're in multiple class. But let's just think about one class. It's either 0 or not 0 in this case. So after the discriminator, if you only train this thing, it tells you exactly what the real answers are. But to generate fake samples, we usually start with k.jpg. All right, Abu send me a picture. Yep, okay, let's go back to that later. Okay, so this is what it was called, latent variables, right? Latent representations or something. Yeah, latent random variables. Okay, it could be just random noise. So every time you generate a new kind of noise, it starts with a different set of parameters. So this is where your randomness comes in. And then that's actually the only part of randomness of this network. Okay, so the generator undergoes the deconvolution that, what is it, that Charlie talked about. And then you're basically transforming this into a new picture. So the same input into a different, but same sized sample. This sample then passes through the discriminator. So there's some, why is it adversarial? Like, why is there a competition? Is that if you look at these two branches, they're all learning the same thing, right? The objective function is only here. So you only know the result once you get to the end. If you're able to generate something fake, and then this discriminator memorizes it, it's no longer, it's going to ignore the true labels. So usually you want to train the generating set more than the true data set. Let's look at the objective function. All right, it's that. Is there a better picture of that? Okay, it's kind of small, but I think it makes more sense if we just, you guys can take a look at this. Maybe it's a better explanation there. So I think I'm better at explaining the functions than the abstract idea. I think this thing explains the idea pretty well. So I'm just going to go through the function. Basically, let's have it side by side. Where's that picture? Okay. So there are two functions, right? Two networks. G is the generator and D is the discriminator. So let's talk about this. This function means we are updating theta G such that this whole thing is minimized. And then max theta D means we are changing theta D such that this is maximized. Okay, so since we are minimizing and maximizing alternatively, it becomes a minimax problem. And with, so let's look at the first stage where we maximize the inside by changing theta d. So theta d means the parameters inside the discriminator. So we're trying to make this discriminator flexible such that the expected value of discriminator of x, x is the real world images. The log likelihood of that is as large as possible, right? So, and then at the same time, I think it's easier to start here. So let's look at the generator first. So Z is the noisy input. So we first generate something, and then we want it to also go past the discriminator. However, it's the imitation of the real input. And since we know it comes from generated data, it is a fake input. Therefore, we want to do the, since this is the probability we predict it to be that given class, the one minus of it to be maximized, right? Essentially, we want this to be good. However, we want this loss to be small. So maximizing this, but at the same time, minimizing that, right? But how do we maximize that? There's no metric to measure whether this is a good fake data. We can only measure whether something is good at the end of the network when we compare loss, right? So there's no way of telling whether this is good until we hit the end. So that's why we sometimes maximize this and we sometimes minimize this. I don't know if it makes sense.
Like the KL divergence extension makes more sense usually with the I think you're familiar with it.
Yeah, okay. So KR divergence.
So I would like to explain. So the reason why GAN is introduced is for introducing these ways of creating new images. So in the paper, if you read the actual paper for the generative adversarial networks, the reason why they use these generators and discriminators that create similar images, and their objective is to somehow learn images that are similar to each other. And what they do, they use this loss function as a way of actually approximating the KL divergence. And they show that this loss function, when this, let's see, what log of, you want them to have a perfect situation would be the generator and the discriminator are at 50-50, right? Is that right?
Like the ideal is that this generates something that's really similar to the real world image, but you can still classify it as a fake image.
Okay, anyways, I was saying is that they're both creating images, but you want these images to be similar in the sense that their mutual information is the similar. And what this it means is to compare their KL divergence, and you can look that up if you want. But so these generators and discriminators are creating new distributions for images that are meant to be similar. And to do that, you want a generator that is you want one that's creating images, and discriminator that is one that's maximizing. How to explain this?
Yeah, I think KL divergence involves distribution, which is hard to explain. I think so basically you want to generate stuff that's similar to the real images, but also at the same time you want to be able to detect that some of this is fake and some of this is not. So if you look at the minimize function, you can actually ignore the first part of the objective, right? So that's when you learn. So how do you learn g? So let's take the derivative with respect to theta g on this. It ignores the first part, and then you're only left with, so you're tweaking g as much as you can such that it minimizes loss on the, what is it? On the whole network. So since we know that this is a fake image, we're doing 1 minus the prediction, the predicted loss. And then, so let's say this is 0, right? Let's say the discriminator says it's a fake image. Your value here is maximized, right? Log of 1 is better than log of 0.5, right? Log of 0.5 is a negative number. So in order to minimize this, we want d to be as close as 1 as possible, right? So what does d equals 1 mean? D equals 1 means d thinks this is a real image, right? So we want, so at the minimized stage, we want this this generator to generate something that looks real, is the minimized step. And then the maximized step is we want to want this to be real and then this to be false, fake. And then we do that alternatively. I think the ratio is usually you do 4 times of this, the top one, and then 1 time of the bottom one. And that is going to give you, so at the end, once this network is trained pretty well, you can take this sample and it will look really similar to real world images. And that's when you can combine that. You can just take that as the output for applications. All right. Let's think about something. Oh. All right, an image kernel is a mathematical operation. Interesting effect. Yeah, okay. So an image kernel is usually a cross correlation. The convolution is pretty much the same. It just takes the mirror, a horizontal mirror of the mask, and it does the same thing. So for some reason, the convolution works better than correlation in images. So they don't use a correlation layer. They use a convolution layer. And since images are usually 2-dimensional, we're going to need a 2D mask as well. So the idea of sliding can be misleading. What the kernel operation happens is only on one mask. So let's say this entire image is just 3 by 3. Your convolution is when you flip this mask horizontally, and then you multiply each element-wise, and then you sum them. So very, very similar to a dot product. Yeah, I think the merit is it captures spatial information useful for classification. All right, let's going back to beginner basics. More explanations on how to display uses of data. Oh, okay. Yeah, let's display the architecture of a neural network using TensorBoard. You guys should try TensorBoard Playground. I don't know if I did this. Okay, so I'm gonna put that in the chat. I think it's pretty intuitive. We're trying to do a classification task, and then the data is 2-dimensional. You can imagine this is height, this is weight. Yeah, exactly. So, I mean, you just have to press a button and you can see some effects. So, what is the true solution to this function? Should be I think it's implying a perfect circle is the ideal solution to this data set. I mean, it's only suggesting that it's not really, like nobody knows what it really is. But as you train, for every epoch, you're updating weights, right? There are very few weights. There are only a couple, so 2 times 4 plus 4 times 2. There are only 16 weights. Actually, there are 2 more here. It's 18 weights for it to learn a circle boundary, right? So this has an activation function. You can try a different kind of activation function. So I guess, ReLU is non-differentiable at 0, so you have these sharp shapes, right? And then tanh, what was that? I think it was like a, I forgot what this is. Oh, it's sinh divided by cosh, right? Okay, so it's smooth, and then at the end you can see the boundary corresponds closely to the activation function. Like sigmoid is similar. If you linear, that's where the problem comes in. Linear, this is a prime example of a model that's not descriptive enough for the data. So our data has nonlinearity in it, right? Obviously, a circle is not linear. It's not linear. So,
you can look up a picture of certain types of loss functions. It's easier to explain.
Yeah. Wait, what did you say?
Look up a picture of all the loss functions in picture form. I don't know.
Oh, like right?
On ReLU, all the activation functions.
Okay.
So if we wanted to talk about, I guess you can talk about some of the properties that make these really nice. For example, if we take sigmoid and tangent, that hyperbolic tangent, the reason why these use are is because they have really nice derivatives and they're really easy to compute. And the advantage of sigmoid is that it's bounded between 0 and 1. But at the same time, you can see that at the ends of it, as you go towards 0 and 1, the weights will kind of just saturate. I think similarly with hyperbolic tangent, the reason why ReLU kind of works is because it's an unbounded activation function, and the reason why it's still non-linear by definition of being non-linear, even though it's connected by piecewise linear. The reason is because, for example, if you take f of 4, for example, the value is 4, but wait a second, is that right? The reason it has to follow by the definition of being nonlinear, if you take f of 4 equals 4, But at the same time, f of -1 plus 5 is 0 plus 5. So inherently it is nonlinear and works as a nonlinear activation function. So when you're able to use nonlinear activation functions, it allows the network to learn things that are non-linear. I don't know how to explain that. The leaky ReLU is a new thing where instead of making it saturating at 0 in X, it adds a small coefficient that makes it a small coefficient to make it more, I guess, slanted. And the reason for this is something called the dying neuron problem. And the problem is that with ReLU, what happens is as you use this activation function, a lot of neurons will just die out to 0. And to prevent that happening, they introduce this coefficient that makes it nearly 0, but not 0. But at the same time, ReLU, you want some of these neurons to be 0 because it allows some sparsity in the network. And it's not reasonable. It might not even be reasonable for all the neurons to be activating at the same time. So it's yeah, I guess these just describe all the types of networks, types of activation functions.
Yeah. Yeah, I think if you're interested, read a little bit about the leaky ReLU. It solves something related to numerical problems, I think. Anyways, yeah, essentially, what separates like ML multi-layer perceptron from linear regression is that you have nonlinear functions in the network. So there's that playground thing. Oh, here. So actually, if you use linear here, this entire thing is a regression, a linear regression, right? No such term is nonlinear in any of these. So if you simplify this, the answer is x1 times this, x2 times that equals prediction, since the activation is linear, right? So you're not able to have nonlinear shapes on the boundary. But if you add, so this is, what is it called? This is kind of the kernelization of your dot product, right? So if you do if you define the dot product between x1, x2 as x times x plus 1 squared, you would have 6 terms, right? At the end, it's able to, even with the linear activation, you're able to have nonlinear boundaries. Okay. Display. Yep, this will work too. So to make a GAN, right, you need a training set of the object you want to make. Otherwise, you can take a pre-trained one. They have the Keras version of it. Unfortunately, they usually just have digits where you generate sort of loss on that, and then you're able to generate other digits, handwritten digits. Yeah, if you want to run it on your computer, clone this GitHub, run these, and you're able to see it. If you want to generate stuff you're interested in, for example, you want to generate people's head, you will need a set of that person's head to train on, and then you can generate that. I think people do that with like Kanye West, and you will need a lot of his pictures before you can generate it. Oh, topical tutorial. Okay. This is a really good book. It's not a book. It's like web interactive. Very simple. Every one of these has like one example. It takes like 2 seconds to learn. So I recommend you just go over stuff that you're interested. Um, yeah. All right. That's about it. Details on different libraries. Um, oh yeah. We're able to open up Jupyter Notebook, right? So let's just do it simple. So different libraries we can use. Say image processing techniques. Okay, let's do an example of image processing, and then when we're doing that, we're probably running into a bunch of libraries, right? So let's say I want to do this that we just saw. You usually go to a GitHub that has these kind of things, and you can just clone it, and then you can run it on your laptop. But there are other. I think a lot of things you come across online is like OpenCV tutorials. They make it so it's very easy to make application with. Yeah, you can just go through one of these videos, but it's more application clean than doing research. They have these very nicely packaged libraries. So I think for OpenCV is CV2, right? So with that library, you're able to quickly read images, do processing on it. I mean, you can literally follow this. Yeah. So OpenCV has a bunch of traditional image techniques, such as I think one just saw like camera calibration, right? Camera. So camera calibration, basically, you have an image, you're essentially looking at it from a different angle after the calibration. These are very old methods without machine learning, but if you're interested in, you can take a look at more. And then there's a class called computer vision at UF, right? That Vimuri, he's pretty good. You guys should check him out. Okay. The only reason is okay. I think for new Python users, or you're not interested in coding, but just some general ideas of machine learning, there are some tutorials online, or the ones we recommend. Yeah, I think just read some blogs, or there's not a particular book that teaches machine learning well. They're either very math heavy um, or like very code implementation kind of stuff. So if you want to just relax and learn, I guess blog posts is the best way to go. What do you frequently use in research? Oh yeah, I don't know. Can someone teach me how to use Hypergator? um,
Actually, that is my presentation for the next week.
nice. Yeah. Okay. Well, we'll see you next week then.
I mean, I know some stuff now. I don't know what exactly you need.
Oh, I don't know anything. Just start from the beginning.
Do you want to log in into your account or?
Oh,
I don't think Jason has a hypergator.
yeah. I don't have an account, but I mean, it's good to know how to use it.
I mean, anyways, next week I will have a presentation about that.
Yeah, that would be great. Thanks, man. Okay, so so imagine you log in. So this is the lab server, right? It's basically just a computer in a lab that's open all the time. That's a server. Also, so how do we interact with it? This is the desktop of that computer, right? My laptop has a desktop like this, but they don't have a graphical interface. You just have to deal with this. Some common Linux command will help. L. And then I think Dr. Fong talked about this, the right axis. I think the color corresponds to your access permission. Yeah, you see that the blue one means this, and the not blue one means something else. Anyways, you can see that your research will, if it involves computing, you're eventually going to go on this because it runs kind of fast on this, and also all the code is, belongs to the lab, so it goes here. There are environments you can activate, right? So then you're running on the correct version of Python, and I think MATLAB as well, right? Oh yeah, MATLAB doesn't have a version. I just opened up MATLAB. Damn it. Yeah, so you can do it here if you don't have MATLAB at home. So let's talk about file sharing, right? There are a few. Well, let's navigate through this server a little bit. So let's go to the root directory. And then there's something I want to talk about the memory. So this is a little bit about computer science. Within an operating system, you have fast memory and slow memory. Our desktop runs on fairly fast storage memory. And then there's also a hard disk. So our desktop, you can imagine it runs on a solid state drive. Basically, it's faster storage memories. It ranges between 250 gigs to a terabyte on your local machine, but on the server, it's a bit bigger. That is our home directory. So as you can see, they're usually on the server, it's like 3 to 4 terabytes, but on your laptop or your desktop, it may be like 200 gigs. These are faster than hard disks. Hard disk drives are slower storage, but they have a lot larger volume usually. So let's say you have images for research. You usually put it in the slowest memory, the hard disks. Hard disk drives are cheap and they have very large volumes. You can put your PNGs in there. There's also like RAM and stuff, but I guess it doesn't matter. Also, if you want to check what processes are running, there are a couple commands like top, so you can see who's running, and if it's in conflict, communicate with them, or and if someone shut your stuff down, or you accidentally run something that conflicts others, you can check here and then see what the problem is, so you can solve with them. So there's something that's harder to experiment on your machine, is the GPUs. I don't think everyone has GPU like right off the bat, unless you're just accidentally on an NVIDIA machine. I didn't have an NVIDIA machine even when I was using Windows, so it was kind of hard to start with GPUs. And also, if you have a Mac, you definitely don't have this. So when you're so there are some code on the GitHub. I think Muhammad is on the task I'm on. Some of the code only works on devices that has GPU. They're usually like CUDA and they're like MVCC kind of stuff. That code is not going to run on your local machine. So to avoid, or if you want to experiment with the GPUs, like parallel computing related stuff, I guess it's a good idea to try on the server so that everyone can, get their share of the experiment, the experience. Like, what was that command? It was like CUDA device or something. Yeah, so with PyTorch it's this. So it doesn't have a current device. So I don't know what to talk about. I feel like it's pretty clear. Is there anything we need? Yeah, I think that covers everything, right? Oh, Docker, Linux. Oh yeah, a little bit about Linux. Let's go to. There are a couple commands. Let's say I want to edit anything in here. I have code in this file. Obviously, I have a .py file somewhere here. How can I edit this file? Some common commands are nano, right? This is a dumb way to do it, but I'm used to it, so I don't want to change. So it's a simplistic kind of editor. But if you never use this, I suggest you use Vim. Vim is quicker to move the cursor and then do a lot of cool things. But if you want to print the file, there's a cat command that prints the file details. So I think the main problem with Linux terminal is that it's very hard to have any graphical user experience. Everything is text, so it's kind of bad. All right, so let's talk about code sharing. So I recommend everyone try GitHub if you're writing code. The main reason is a lot of resources on GitHub, and then most of the research, if you want to go down to the details, it's very easy to just look at code than look at paper, because papers can be ambiguous. The words, sometimes even the graphs they have is different from the code they run. For example, yeah, I think so. Let's try to see. This paper has. Oh wait, that's this paper. So I think a good exercise is, so when you read about this, then they explain how they do the optimization. And then it seems ambiguous, like, this line, the other line, and then you wouldn't know, the correct way. You can just check their GitHub. And once you're comfortable, I think you can go into the corresponding file, and then look at how it's actually translated. So basically, these 4 lines corresponds to something in the code, and if it's ambiguous, you're able to um, you're able to do the same thing they're doing. Otherwise, you might be making a mistake, and then your experiment will not be consistent with their result. Anyways, so if you want to contribute, the command for cloning the repository is git clone. And then you're able to see their files on your system. So I think before we run this, let's see if they have any requirements. The only thing they need is Python, PyTorch, and TensorBoard. That means all we have to do is to run the main file. And this is where all the errors comes in, and you might spend like a ton of time debugging. For example, I don't have this, and I then have to install that. TQDM, what the heck is that? Progress bar, wow. Uh-huh, can't even install that, can I? So I think what I need to do is delete that. TQDM as bar. Get out of here. I don't need that. Oh, come on. Okay, so the whole thing is related to that. And so this is where the libraries becomes hard to manage. It involves a lot of experiment with pips. Oh, okay, so I guess my pips problem. All right, just kidding. We're lucky it works today. Yeah, I hope it doesn't use its GPU, so I can run it on your. Yeah, okay. So in this particular example, we need a data set to train on. So this GitHub doesn't run on itself. It provides you with a template so that if you insert your data here, for example, you're doing CT images, you set it up here and then do some plumbing related to this, and then the GitHub would work. So this is like a semi-product of that's flexible with any kind of data set. However, I feel like people are just more curious about where is that? Yeah, I think people just want to do image processing. Then it's easier to do with OpenCV because they have a better pipeline than PyTorch. Okay. Is there anything else? It's a good time to stop, right? All right. So to summarize today's, we just talked about a bunch of random things, and so I still recommend you going through this tutorial. So I think you'll learn more if you go at your own pace. But I think I talked about some, easy stuff that can be done through this session. All right, that's summarized today. Thank you everyone for coming. I will meet you guys in the next meeting. Oh, is there any questions?
Actually, I have a question. I tried to install TensorFlow, and now I try different methods. I search on YouTube, and every time I do it, I have an error when I'm supposed to import TensorFlow.
I gotcha. This is what I'm good at. It's just a bunch of plumbing. You want to share screen?
Yes. Let's see.
Yeah. So this is not really anyone's fault.
Just don't look at the left side, it's something else, but here you can find it. Yeah.
Okay. So
Keep going down. Keep going down.
yeah, go down to the DLL. You're on a Windows. Okay. I recommend you install with Anaconda. DL load fail is basically something is not linked when the library install.
Actually, it might be your Python version.
Yeah, you could also switch.
No, I think Python 3.7 is not supported. Is it?
Yeah, but this is 3.7, right?
Well, I'm saying that they're the newest, as new versions. I don't know, certain versions of Python might not actually be supported.
All right, so this is what you need to do. It's pretty convoluted. First thing you need to do is check the version of TensorFlow. So do this. Do Python, the Python you're running, pip list, or did you install with pip?
I tried different methods. I've tried with Anaconda, with pip install. None of them worked.
I see. So what was the last one you tried? Did you use Conda or did you use pip?
I think I used pip.
Okay, so you do this, and then check the version of TensorFlow.
Are you sharing the screen or?
Oh, I just sent.
Oh, okay.
So all right, so essentially you want to open up Python, and then you can import TensorFlow without error. So this is eventually you want to do this, but there are a couple of versions you need to do. First, you need to check Python version, and then you also need to check your TensorFlow version. Your TensorFlow version is here, right? I don't know what yours is, but if it doesn't work,
that one. Yeah.
Yeah. What's the number?
I don't remember, but I know it's not that one. Wait, let me just see which one it is.
Yeah. So you just run this command, and then it'll tell you. The next step is to go on their website and see if it supports it. Since you're also on Windows, right?
Yes.
Yeah, on Windows, it also requires Visual Studio support. Yeah, this is why it's so hard on Windows. I fucking hate it.
Mine is 220.
220. Okay, yeah, that's newer. I don't think that's the main problem. The main problem is probably this. You need, on Windows, you need Visual Studio support for C++. So do you have Visual Studio?
I don't think so.
Yeah, okay. Just to confirm, you can copy and paste that DLL error. I think it's going to ask you to install Visual Studio. If you don't want to do any of these, there is something called Google Colab Online.
That's actually what I used. Yes.
Yeah. Do that. On Windows. Okay, another way to get around this is to use Anaconda. Pip and Windows is a bad combination because of the linkings. It's super annoying. I know it's there's no easy way.
Yeah, but Colab is also fine.
Yeah, so Colab uses libraries on the cloud. It doesn't use your machine, right? So the computational resource on Google Colab, they actually give you the sandbox of all the, like it's not really running on your laptop. The only thing it uses is the browser resource. It doesn't use your GPU. So you can import TensorFlow here. And you can check the version of it. It's not going to be the same as your version, right? 0.22, but obviously I'm on a 2.0.0, right? Yours is just on accident the same as theirs. So for it to work, you need to use Anaconda or install Visual Studio.
Okay, makes sense.
Yeah. Okay.
Thanks.
Yeah, no problem. Yeah. So guys, if you use the lab server, it has everything already configured. So if you don't mind using command line interface, do that. Okay. All right. Thanks for everyone for coming today. I guess I'll see you guys next week.
Bye.
Bye, everyone. Bye.